We now interrupt your scientific broadcasting for a message from our imaginary sponsor. At Apple, we always strive for innovation. That's why we have reinvented the way you browse the web. That's why we have fundamentally changed how you listen to music. And that's why we revolutionized the amount of money you are willing to spend on a stand for your computer monitor. And now, we're doing it again. We've made the biggest change we have ever made to the iPhone. We shrunk the iPhone down to the size of a matchbox. This change is so huge and revolutionizes the world so much that it will be the standard for years to come. To show this, we don't call this model the iPhone 12 or even the iPhone 12 XS. We call it the standard model. Welcome to Fundamentally Explained. Here we try to uncover the mysteries of the smallest building blocks of nature. Our best knowledge about these building blocks, these particles, is encoded in the standard model. The standard model is a theory that makes predictions about the properties and the behavior of these particles. Now, I would be the last one to say that it is an easy theory. To work with it, you need a strong mathematical background. But if you don't want to work with it and just want to understand the general ideas behind the standard model, I think you don't have to resort to mathematics. I think it is possible to understand the general gist of the model without having to execute a single calculation. And that's what we will do today. We will explore the basics of the standard model without mathematics. The goal of the standard model is to describe particles. So if you want to understand how it works, you need to know how these particles work. In an earlier video, we saw that particles are waves, and waves can be described by keeping track of their energy. Yeah, energy, man. Everything is made up out of energy. We're all connected by the same positive vibes. Let's all share our positive energy and let's stop spreading the negative energy, dude. Yeah, let's do that. But the energy I am talking about has nothing to do with that. Nor has it anything to do with auras or chakras or flows in acupuncture. In physics, energy is actually quite well defined and can be seen as a sort of budget, the amount of oomph to do stuff. Everything has a total amount of energy associated with it. It can be stored in the form of warmth, in the form of movement, or even in the form of just existing. Even being higher up, say 1 meter above ground, can be associated with an energy, namely potential energy. It turns out that all types of energy that you can identify are either a form of this potential energy or a form of movement energy. This is already quite weird, but an even more peculiar property of energy is that it cannot be destroyed or created. The total amount of energy is constant. The only thing that can happen to it is that it shifts from one form to another. This makes energy quite a nice property to use in our model. Particles can be destroyed and created, but energy can't. To describe particles, the standard model therefore uses this energy. It's just easier to keep track of something of which the total amount does not change. Knowing this total amount is, however, not enough. To find the dynamics of particles, you actually need to know how the distribution of this energy changes over time. A nice quantity that does this for us is called the Lagrangian. The Lagrangian subtracts from all movement energy all potential energy. There's quite some rich mathematics behind it, in where the minus sign comes from, for example, and how it can be used to find the exact evolution of particles over time. But for simplicity, we will ignore all that. Instead, we will just use it as a recipe. Subtract from all movement energy all potential energy to find a description for your particles. To show how the standard model is built up from this framework, let's use it to build a model of our own. To keep it simple, ours will only describe the behavior of electrons. And yes, we are ignoring 16 particles by doing that. I know, I'm sorry particles. But they will get their own video someday. For now, focus on electrons. What do we know about electrons? Well, we saw before that electrons are waves in a field. So instead of describing every individual electron or every individual wave, let's use the field in our model. A field is, mathematically speaking, a bit like a map. It's a thing that gives to every location in space, at every moment in time, a specific value. A map like this one, for example, gives for every location, for every point in space, the elevation of the land with respect to sea level, which is just a number. Our electron field might not be a description of heights, but of electron waves, but the idea is still the same. It's just a thing that assigns a number to every point in space and time. We wanted our model to work with energies, so let's add the movement energy of the field, that is stored in the waves of the field, to our model. Bam! We are not done yet though. As you will see, it takes quite some effort to create a model like the standard model. It would therefore be a shame if, at the end of the day, it only worked at a specific place in space or at a specific moment in time. I warned you not to mess with us. No, please, don't do it. Please don't do it. Don't, please. No. The results of our model for a specific process should therefore not change if the process happened at a different location or at a different time. This is a bit like a deck of cards. To avoid hassle, you want your playing cards to look the same upside down as they do upside up. In other words, your playing cards should be the same when you rotate them by half a turn. Or to say it more physicsy, they should be symmetric under these rotations. For our fields, we might want these symmetries as well. We could, for example, try to add a symmetry that makes the results of our processes it describes not depend on time or place at which processes happen. But time and place are just a choice here. We could make the model symmetric under changes in electron properties. Which and how many of these symmetries we add to our model is essentially a choice. We need not add any symmetry at all, but if we add a symmetry, something unexpected happens. To see this in action, let's step away from particles for a moment and let's look at clocks and trains. Give me a second, this will all make sense. Imagine you are traveling by train from city A to city B. You depart at 12 o'clock and after arriving in city B, you look at the station clock there and see that it says 1:45. How long did your journey take? 45 minutes, right? This calculation is pretty straightforward and works no matter your departure time. Even if we would all agree to move our clock 1 hour forward, as many countries do during summer, you would still find 45 minutes for your travel time. This is called a global symmetry. Your results do not change if everyone agrees that we change the time in exactly the same way. But what if you tried to do this experiment before the end of the 19th century? Back then, every city had its own time convention. Clocks were not synchronized at all, meaning that, for example, 12 o'clock was at different times in different cities. In this case, your travel time calculation would totally break down. Let's make this extreme and say that a clock in city B runs 45 minutes behind the clock in city A. If you repeat your journey and leave the train in city B, your careful calculation would tell you that you traveled for 0 minutes. Our calculation, our model of travel time, is thus entirely fudged up by local changes in time definition. We say that it might be globally symmetric, but not locally symmetric under changes in time. There are 2 ways to handle this. The first one is to say that local changes are just not permitted. The second one is to alter our model. If we choose to alter our model, and say that we indeed choose this, then we need extra information. In addition to knowing the time in city A and city B, we now also need to know how the time convention changes when we travel between cities. Taking into account that in moving from city A to city B, there is an inherent time difference of 45 minutes, we can correct our model for this. We will then again find the correct travel time of 45 minutes, as we did before. Okay, but what can we learn from this for our model of electrons? Well, it means that if we want to make sure that the results of our electron model do not change when we make local changes to some quantity or to some property, we might be able to do this by adding extra information to our model. Let's just try this out, and let's choose, for the sake of argument, that our model should be symmetric under changes to the phase of electron waves. Very simply put, the phase determines the timing of the up and down movement of our wave, like a sort of an internal clock. We want our model to not care about the changes in this phase of our electron fields. And not just about global changes, but especially also about local changes. Just like with the train example, local symmetry is not an inherent feature of our model. If we do the maths as is, the model just breaks. So we need extra information to make our model continue to work. This information should tell us how the phase of our wave changes when we walk from a point A to another point B. As there is no reason to define the locations of either A or B, we should provide this translation value for each point in space and time. A thing with a value for each point in space and time. Where have we seen that before? Our electron field. This extra information on the electron field is a field in and of itself. A field that translates between the phases at different locations. Let's write the translation term for our Lagrangian like this, so that it is clear that it translates between the phases of different waves. It turns out that this term is a type of potential energy, so we add it to our Lagrangian with a minus sign. For completeness, let's also add the movement energy of this field to our model. Note what happened here. We required our model to be symmetric under local changes in a property of the electron. To make this work, we had to introduce a new field. A new field, so that also means new particles. As in, a new type of particle. Not an electron, but a particle associated with this new field. Now, when I first heard this, I thought, yeah, okay, might be. But this whole endeavor is just a trick of theorists to get their silly theory to work. It's just a trick. It's not real. But no, as it turns out, the particles of this new field we just added are actually seen in experiments. Quite literally, because these particles form light. Friggin' light! We barely did a thing. We only assumed that there are electrons and that our model should be locally symmetric under changes in some electron property. That's it, and ta-da! Light exists. I don't know about you, but I'm always a bit flabbergasted when I hear this. And on the first day, God created heaven and earth. And God said, let there be invariance on the changes of phase such that quantum field theory behaves nicely under local changes in its value. And there was light. And with this we have now covered the entire recipe for the standard model. Take an empty Lagrangian, add fields as subjects, and symmetries as extra requirements. The full theory of the standard model contains 17 fields, 3 of which are the result of added symmetries. This results in quite a large formula, but we don't have to look at that for the moment. The core ingredients are still the 3 we saw before. Note, however, that we had to define ourselves which field we started off with and which symmetries we added to our model. As far as we know, there is no way to get the fields or symmetries from core principles. This introduces a certain degree of arbitrariness when you create your model. Which fields and symmetries you add is totally up to you, as long as your model ends up internally consistent. In fact, playing with the specific fields and symmetries is something that is the core of the work of theoretical particle physics. It tries to answer questions like, how does the theory change if we add another symmetry or a specific field? Is it possible to make the standard model even better by adding an extra line to the Lagrangian? Would we expect the existence of a new particle if we add this line? And if so, how can we measure this particle? Anyway, now that we have our Lagrangian, our model, how do we use it? Well, the first step would be to look at the terms that we've created, and specifically at the parts of the formula that contain multiple fields. What does this combination of fields, for example, actually mean? We started off our journey by saying that the total energy of our system has to remain constant. Energy cannot be destroyed or created. Now imagine we have a single wave of light that has some amount of energy. As a result of this combination term, the energy of these particles can move from the light field to the field of electrons. Without this term, there would be no connection or interaction between those fields. Combination terms like these are therefore called interaction terms. Interaction terms allow energy to be transferred between fields, so that in this case energy of a light wave can be used to create two waves in the electron field, effectively changing a light particle into two electron-like particles. Wait, what? And this is not even the only possibility. A single electron can also just split a bit of its energy off in the form of a light wave, or two electron-like particles can come together and form a single particle of light. All these different processes are possible due to this single term. You can see it as a sort of a puzzle piece with 3 legs. It can be rotated in any way you like, and you can even connect it to other puzzle pieces. By connecting 2 of these puzzle pieces, you can, for example, describe 2 electron-like particles that turn into light and then back, or a single wave of light that briefly changes into 2 electron-like particles and then back into light. Diagrams like these, that you can make by connecting puzzle pieces, are called Feynman diagrams. These diagrams are incredibly useful, as they can be used to calculate all kinds of things about the process in the diagram. For example, how many times you expect to see this process in an experiment. To do such a calculation, you analyze the diagram by looking at what kind of parts it contains. These parts are the interactions, but also the connection lines between these interactions. Mathematical expressions for any of these parts can be extracted from our Lagrangian. Combining these expressions then creates mathematical formulas that can represent all kinds of interesting information about your process. The evaluation of these formulas can, however, be incredibly complex. So complicated even that literally nobody knows how to solve them. Nevertheless, this is the general idea. To learn something about the process, you connect puzzle pieces to create a diagram. And from this diagram you extract a mathematical formula. Now, of course, the full standard model is a bit more complicated than just electron-like particles and particles of light. The standard model contains not 2, but 17 particle types. So the number of puzzle pieces you can work with is much, much larger. That changes, however, nothing about the fundamental idea behind the theory and its construction. The standard model tracks the distribution of energy in fields. Some fields are introduced at the start, while others turn up as a result of symmetries that we require of our model. The interaction between the symmetry fields and the particle fields results in puzzle pieces that we can use to create diagrams. And for these diagrams we can then calculate, for example, how likely they are to happen. And that's a wrap. The basics of the standard model explained without mathematics. I honestly did not intend for this video to be so long, but I hope you liked it anyway. If you did, or if you didn't, let me know in the comments down below. Oh, and while you're down there, let me also know which particle physics subject you would like to see covered in a future video. I promise I will make it completely understandable, as it will be fundamentally explained. See you next one. To show this, we don't call this model the iPhone 12, or even the iPhone 12 XS. We call it the standard model. Thank you, thank you, thank you, thank you. Not only is the standard model the smallest iPhone we've ever created, it's also the strongest iPhone we've ever created. To show this, I would like to invite Derek to the stage for a demo. Derek? What is this? A model for particles?